Hi, everybody. Thank you so much for joining us today. My name is Jennifer McConnell. I'm the product manager here at Protochips. And today we begin our new webinar series called Closing the Pressure Gap. And it's focused on doing high pressure gaseous experiments, looking at gas-solid phase interactions within the transmission electron microscope. We're highlighting how our atmosphere AX system supports heterogeneous catalysis research at the nanoscale. Although it should be noted that's not the only area of research it supports, but it is a big one. Because catalyst materials are typically in nanoparticle form, the TEM is really an ideal characterization tool with its powerful resolving capabilities. But the characterization of static materials before and after a reaction doesn't necessarily lend insight into the mechanisms that lead to operational changes in the catalyst over time. Over the years, technology evolved in an attempt to introduce gases safely into the vacuum chamber of the TEM in order to watch these materials undergo these mechanisms under a more realistic environment, with hopes of really getting some direct insight into how their structure really affects their function. Now, the pressure at which these experiments are performed can have a big effect on your results. And so this webinar series is meant to give you a glimpse at what's possible today to create realistic high pressure environments within the TEM using our machine vision based software-based system, the Atmosphere AX system. If you're not familiar with our company, just a quick, Protochips, we choose to focus on the entire workflow for in situ TEM. It's not just about providing TEM related hardware, because everything from sample preparation to the accuracy and robustness of your in situ parameters to your data collection and data management, all of that can affect your results. And that also affects your ability to properly scale from bulk down to nano with relevance, can affect the reproducibility of your experiment and your productivity as well. So keep in mind, your success lies in addressing the entire scientific workflow, and it's not just about the hardware itself. So we're really grateful to have you here. And before I introduce the star of today's webinar, I have a couple of housekeeping items to cover. Everybody here is muted due to the audience size to prevent unintentional interruptions while our speaker is presenting. But if you have questions for him, please enter them into the questions box and we will ask him at the end during our Q&A session. There's also a short survey that pops up after the webinar. We would greatly appreciate it if you quickly fill that out for us. And there's also a certificate of completion that will come in your email after the webinar if that's something you're looking for. Okay, without further ado, let me introduce our speaker and our star today, and then I'm going to hand the mic over to him. So we are so lucky. We've got Dr. Lawrence F. Allard, and he's a distinguished research staff member at Oak Ridge National Laboratory, and also a fellow of both the Microscopy Society of America and the Microanalysis Society of America. As an early collaborator with Protochips, he really promoted the development of MEMS-based in situ heating and gas reaction capabilities to help advance these technologies in the field of electron microscopy. His experience with in situ gas reaction studies date back to 1965 as an undergraduate student at the University of Michigan, which led him ultimately to obtaining his PhD also at the University of Michigan. Larry, we are so excited to have you here. Thank you so much for joining us. I'm going to hand the mic over to you, and whenever you're ready, you go ahead and get started. I'm going to hide myself because you don't need me.
Thanks, Jen, and I appreciate the opportunity to give this presentation. I've done it, as I said, 1 or 20 times before, parts of it. So some of you who've been to talks that I've given in the past on in situ work will recognize some of the slides. So this is a 60-year retrospective because I've been doing it for almost 60 years, 59, let's round it up to 60. And there we go. Number of collaborators are represented in the slides that I'll be showing today, and including a significant number of the crew from Protochips Company. And there's just a couple of talks, parts of the talk, part 1 and part 2. The first part is the historical perspectives, how we did it in 1965. So I'll be talking about in situ gas reactions to start with, primarily for copper oxidation studies, and this is going to be historical in nature to show how that what the lead up was to doing these kinds of studies, and then how that factored into my getting involved with Protochips about 40 years later. So part 2 will be 2006 to present day development MEMS-based technology, both the fusion and atmosphere systems will be discussed. So I was an undergraduate, as Jen mentioned. Professor Bigelow was teaching the electron microscopy course in the chemical and metallurgical engineering department at Michigan in 1963. And long story short, he invited me to take his course as a sophomore, and it was a graduate level course, pretty intimidating. This is Professor Bigelow in 2013 at age 90. He was past president of Microscopy Society in Minneapolis. And my first meeting of the Microscopy Society was 1964, so I was definitely at that meeting. Professor Bigelow was born in 1923, 4 years prior to the discovery of electron diffraction, and he's still active, still doing science. Well, this slide is from 2013, but he's still with us, and he'll be 101. This is a picture from his 100th birthday last March at the University of Michigan. He'll be 101 in about 3 weeks. This is the balloon TEM at his party. Great story behind that. So copper oxidation was initiated at the university by Professor Bigelow's Professor Lawrence Brockway, Professor of Chemistry. Brockway was the second graduate student of Linus Pauling, 2-time Nobel Prize winner, and Brockway was the advisor also of a Nobel Prize winner, Jerome Karl, and Professor Bigelow's PhD was granted in 1951 under Professor Brockway. As I mentioned, in 1963, he taught me in this electron microscopy course. This is Professor Brockway in the year I was born with Jerome Karl. A little bit later in life, as I knew him first in about 1964, holding a picture of Linus Pauling, his professor. There's a great history. And Professor Brockway, by the way, was one of the founding members of the Microscopy Society of America in 1942. Connection with Oak Ridge began as a result of studies that were done on bulk crystals, single crystals of copper in the mid-50s. And here's what Professor Brockway saw when he was as a consultant to the folks at Oak Ridge was this copper sphere that had been oxidized, reduced and then oxidized. You can see some patterns of oxide growth on this sphere. This is an elliptically polarized light picture of these patterns that appeared in this publication. Folks can see this. To prove I'm not lying, I actually have that sphere encapsulated in lucite here. I hope you can see that.
We can see it, definitely.
This is one of my props. This would be a hand around, by the way, if we were in person. Okay, so Professor Brockway saw this copper oxidation work that was done, and this was in the late 50s. And he started having ideas about how to study oxidation of copper in an electron microscope. And his association with Professor Bigelow, who was by then a professor in the Department of Chemical and Metallurgical Engineering, Professor Bigelow obtained funding for a couple of modern electron microscopes. And this is one that was installed in 1962 that had a cine camera. And the purpose of getting this microscope, which, by the way, with all the attachments, including the cine camera, cost $37,000. Big bucks in 1962. And so the purpose of this was to be able to conduct in situ studies eventually. So that led to work that was done starting in the summer of 1965 after I was the primary operator of the microscope during those studies. Just pretty good for 1963 GEM 6A specifications, guaranteed resolution of 12 angstroms. I say in your dreams on a good day, and that was definitely not in making cine movies, hard coupled to the column of the microscope. So here's the cross section of that old microscope, just for historical reference for those of you who don't believe that things like this could possibly ever have existed. There were no electromagnetic alignments. Everything was done mechanically. You wanted to tilt, have some tilt correction. You had to actually physically tilt the gun. You had to physically shift the conventional lenses around mechanically. And that microscope, there was no electromagnetic stigmator. It was all mechanical stigmator. Very much fun, and a monocular to look at the screen. But it did have a large volume that was set above where the specimen cartridge fit in through an airlock, that we could do supply gas into here and put other attachments and so on. That was a feature of this microscope, and it had a top entry specimen cartridge in the objective lens pole piece. So to do in situ work, we made an adaptation for the stage of the microscope where we could put this little insert with our own specimen cartridge in. This is just a sketch of what it sort of looked like. Here's a cross section of our best recollection, I said, of the stage design. We don't have any plans, but this was built by Professor Bigelow and Professor Brockway so that the cartridge fit down in a special stainless steel cone that we could put a homemade heating coil around, and this would heat up the whole cartridge. And the nice thing about the pole piece design was this wide gap, so there was room for all of this stuff and that microscope. To show how compare the heating technology of those days to the heating technology of today, I remembered how I made these things. And so some time ago, I got all the parts together. We had some new stuff called silicone. I didn't need, but I needed this tip here because this tip of the silicone rubber was perfect for winding a nichrome wire, double back for non-induction, and so I could mix up some of this sour-rising cement, put it on this tip, wind the wire around, and then coat it with sour-rising. And after a couple of days with baking and all, we had a furnace. So this took a while to develop and actually make work, and it actually worked. It could heat the whole cartridge up in the microscope to a calibrated temperature of 525 degrees. So just to compare and jump ahead a little bit, teaser for part 2 of the talk, when we talk about MEMS devices, this 1965 heating element, as I said, had to heat up. Took a while to heat up, took a while to cool down. In the case of the new modern heating chip technology, you can get to 1,000 degrees in a millisecond and cool it off just about as fast. But I said it's like a dump truck versus a Ferrari, but the dump truck does things a Ferrari can't do, and vice versa. I don't think there's a way to use a MEMS chip to do the particular copper oxidation studies that we did. So this is actually kind of like an E-TEM, but differentially pumped. It was just, we let gases into the column. This shows the cine camera attached to the plate chamber of the microscope. And to make movies, we ran the film under the screen of the microscope, and the screen had to be replaced. Fluorescent screen had to be replaced by one with a hole in it. Normally, the hole with the screen down would be at the top of the top of the screen, but when it was lifted up to this 45-degree angle, then the beam could come down and hit the film that is running into the screen as you're looking at it, and then back out at you when it was being run through the plate chamber of the microscope. So we would get the image set up and then reduce the magnification prior to raising the screen up, and then the hole in the screen would be in the middle, and we could then record movies. This shows the sending and take-up reel and that was pre-pumped in the plate and the dark room. All the assembly made on the cine camera and then inserted into the plate chamber and clamped down and pumped out. And that was all fun stuff to learn to do back in 1965. And this is the only picture we have of our setup with the home-built gas manifold, glass stopcocks, Baird Alpert and Prani gauges, everything hard coupled to the microscope. And this is me at the column getting ready or doing an experiment back in 1965. So copper oxidation studies in those days, we looked at 80 nanometer thick films that were grown in a vacuum system on sodium chloride surfaces, some grit annealed, some substrate annealed, and we used a measured 5 by 10 to the minus 4 torr of either hydrogen or oxygen in the column. This is letting this gas into the entire column. The entire column was probably in the 5 by 10 to the minus 6 torr range at so-called high vacuum. And then we increased it 2 orders of magnitude, but still not very high pressure because you'd burn out a filament if you had oxygen. And we did burn out filaments. A couple of filaments per week, but we fabricated our own and it was quick to change the filament in that microscope. So here's a frame from one of the movies, and I actually have this movie that I think we can show here. And this is just an example of what was the most fun thing that I've done in my entire life, just about, in 1965. It's been downhill from there, I think, because this was a lot of fun. So you see dislocation, stacking faults, thermal etching. I'm going to speed this up by dragging it across, and you'll see another frame, stacking faults, and then grains of copper oxide growing. This is after hydrogen reduction and then pumping out and admitting oxygen, and so it actually worked. We're actually able to make movies of copper oxide growing, and you can see some influence of the stacking fault on the growth of the oxide. Okay, and here's another one. That grain growing along there, we calculated to be about as fast as grass grows. Okay, and this is kind of lifetime on that. So that's about as fast as grass grows. There are no mag markers on the films, of course. And here's some of the oxide grains. Okay, so this is all clips, some of the best clips from those studies in those days. And at the end, it's got one really nice big grain that you can see here. Again, this was a lot of fun in the summer of 1965 to do these studies. Okay, so that's some of the early work that led up to eventually getting associated with Protochips. So there's the reminder to go to part 2. I can escape and bring up part 2. Oh, this is part 2. That's Kinga's talk. I want to go to the start. And this should be better. Okay, heating experiments in electron microscope part 2. And this is entitled Development of MEMS-based Heating Technology 2006 to the present day. In 2006 is early 2006, I got a call from David Nakashi, 1/3 of the founders of Protochips company, and he said that described this new device that they were able to make based on MEMS technology, where they could use this little silicon chip that had a membrane deposit on it that they could heat to the magic number was 1,000 degrees centigrade in as little as a millisecond. And would I be interested in collaborating with them to develop a capability for doing in situ heating in the microscope? And I said, boy, have you come to the right guy. And I described some of the work I'd done at that point about 40 years prior with Professor Bigelow. The interesting part about this to me was that, here's the outline. AML is the Advanced Microscopy Lab. So I'll describe this a little bit, and then background on MEMS-based technology, in situ heating, and in situ gas reaction studies as part of the talk, and here's some of the collaborators. So we had just in 2004 completed the construction of this laboratory for aberration corrected microscopes, basically at Oak Ridge National Lab, and specialized facilities needed for super high resolution capabilities that were just being developed in the early to mid 2000s. We got one of the first 2 JEOL commercial STEM-TEM instruments delivered the same week as the one at Lehigh, the GEM 2200FS, has these features. And I had, before David Nakashi got in touch with me, I had conversations with my manager and told him that now that we had this microscope up and running, I would like to think about the possibility to develop a capability to do some in situ heating studies in this microscope, ultimately to see what we could see at atomic resolution. And I was thinking more about purchasing a standard 3mm heater for 3mm foils or grids or whatever at the time. And then my sense is that it was within a week, David Nakashi called me. It was like a message from God and coming down that it just happened to hit and started this collaboration. So aberration correction, everybody knows, this is the famous fix of the Hubble, and this is what the electron microscope does for you. And here's the team that in around 2000, mid to late 2007, after we got connected and started with the work with Protochips, and David Nakashi and John Damiano were visiting. Larry and Professor Bigelow and our colleague Steve Bradley at the time, we're looking at an early holder, and so Professor Bigelow built the first holder that was this one was not thin enough to fit in our microscope correctly, so we built our own holder. And Professor Bigelow designed this holder, and let's see if I can move this over so I can see it. Okay, so this was a bench test, and here's a movie. This was first time we actually used and heated this holder. This is out in the atmosphere on the bench, running with this controller, and this is heating to 1,000 degrees. You can just get a feeling for how this works. This was quite exciting to see that we actually made a holder that we could, and they're very robust because they could be heated up in an atmosphere to 1,000 degrees and could do this, thousands of times. We did a couple of early experiments, and this is an early heater chip. They were only about 2.5, 3 millimeters in diameter, and this shows the geometry of the chip, one of the early chips, so that we basically pass current through this electrode from one electrode to the other through this thin membrane, and there are holes in the membrane with carbon film that you could deposit particles on, say. And here's an example. This is, I think, one of our first trials at doing high resolution imaging to see if how this would actually work. And let's see, I think I might have to go to this one. Here we go. So this is platinum, originally platinum. It's just regular platinum nanoparticles on alumina. And about, what, 5, 6, 7 nanometers in diameter. See some of the structure, and it's at 1,000 degrees centigrade. And this is frames taken over a short time because this was changing relatively dramatically. But what you can see is that it looks like it's ordering along the way. Okay, and here's 2 frames. We think this is showing it partially ordered. This is taken at 10 million X at 1,000 degrees centigrade. Again, we were pressing and trying to get the ultimate kind of imaging capability just to get an understanding of what it would do. This was pretty remarkable that we could take pictures like this. But what is this? What is this particle now? It's some kind of ordered structure, and it's definitely not just pure platinum any longer. We haven't been able to determine exactly what doing the fractogram. So we still have a little bit of a mystery on what exactly was going on with this, but it showed the capability of the technology. Okay, so this is an early commercial version of the heater and shows the silicon chip technology in cross section. This again is an early heater device, and you can see the carbon film with nanoparticles put on it. And so about one of our next experiments where we did high resolution imaging was looking at iridium on MgO at 800 degrees centigrade, 10 million X imaging to show how single atoms behaved and clustered up. And this movie I can show. These are just single frames that are put together. You can see how the atoms cluster together and gradually, I'll let it run, join together. And we can get beautiful images of single atoms, again, at 10 million X magnification. So again, just a demonstration of the capability with a heavy element on a very light substrate. And so those were samples that were fairly easy to make, just depositing particles on the heater device. But then we advanced to doing work on aluminum alloys that I want to highlight in this talk. And the question was how to deposit a thin lamella of a bulk alloy onto an E-chip, because we do electropolishing on these foils and normally look at 3 millimeter diameter specimens that have holes with thin edges that we can study the structure. So to be able to look at and get good resolution and orientations in the microscope, you have to have a double tilt holder. And so the early work we did was with a holder that was built by Professor Bigelow, the first version of a double tilt holder that we used to look at grains of aluminum that were sectioned out with a gallium fib. Gallium is bad for aluminum, so we could get predetermined orientation near, in this case, near a 001 grain zone axis of the grain in this image, and we would then section out the grain that we wanted to look at, area that we wanted to look at using gallium fib. In this case, we did gallium fib with a minimum of exposure to the gallium beam using electron beam deposition of carbon to attach the tip of the probe to the lamella that we sectioned out, lifted it out, set it down, used electron beam deposition to tack it down. As I mentioned, this was the thin area. And the problem here is that even with the best case, using the gallium beam to cut, gallium gets everywhere. So this was an aluminum copper alloy and 7% copper. And you can see the gallium in the area of interest, even though we just cut it over here quite a ways away from the area of interest, the thin area of interest, and we use electron beam deposition to tack it down, we still had lots of gallium in the area of interest. So the solution for this was to go to a xenon plasma fib. And in this case, you can see where we did similar cuts. We deposited tungsten using the xenon beam, and even in the area where it's just heavy tungsten, there's very little xenon implanted. And in the area, one of the thin areas, this is the area of interest, but nearby, you can see the xenon is effectively non-existent, and the tungsten, there's a little overspray of tungsten, but just barely shown, way less than the gallium that was present, which is bad for aluminum. And tungsten, it turns out, is not bad for aluminum. Tungsten doesn't move in aluminum at the temperatures that we're interested in doing studies on. So I want to show just an example of the kind of results that you can get with the good technology for making samples. We have a program that developed a new alloy, the ACMZ, aluminum copper manganese zirconium alloy with this extreme resistance to coarsening, and it's due to these precipitates, theta prime precipitates that are on 3 habits of the, like shown in my little model here, 3 habits of the cubic aluminum structure. And so this is looking at the 110 aluminum zone axis, and you can see the edge of the precipitate, theta prime precipitate, and it would develop these with these extra alloying elements, the location of some of the heavy metals on the semi-coherent interface that we've proven tended to keep these precipitates from coarsening at elevated temperatures. So I mentioned the double tilt holder. This is the first generation double tilt holder, the only one in existence now. It had a ±6 degree beta tilt axis. It's kind of the general features for the tilt mechanism for the commercial fusion holder, which is this holder. I think we built this entire holder for about $7,500. So, but it worked. Here's I think one of the first commercial versions of the Protochips CAD designed beautiful double tilt heating holder that is in this case a 4-contact holder. And this, I'll show this animation for the fusion technology, and I'll speed it up here. And this is just how this works. So there's the chip, has some particles deposited and put in the holder, makes good electrical contact. You can have different kinds of chips that allow electrical measurements as well as heating. Put it in the microscope, and heat it up. So when you heat it up, something happens, and you study just the thermal effects on your sample. But you can then do strictly electrical biasing, 4-point biasing, and that chip, and then you can also use chips that allow simultaneously to do electrical and thermal testing. And there's the double tilt mechanism, plus or minus 14, I think 14 degrees tilt in the beta tilt, and similar in the, so there's large tilt. Even, I should mention the JEOL 2200 FS only has a 2mm gap pole piece. So all of these holders fit nicely in that microscope and allow a lot of motion because of the beautiful design. And finally, you can get x-rays out with modern dual EDS STD detectors. And exit that. There we go. So this gives you good stability for imaging and the correct orientation, so you can look at atomic columns. And here's an example of a xenon plasma fib sequence. And this example, these streaks here are actually residual tungsten after tungsten was deposited by incorrect plasma, doing the xenon plasma depositions, we were able to use the xenon plasma beam at 2 kV to clean it off, and it actually ended up being a fairly nice example where you could use these residual tungsten features as fiducial marks. So here you can see these theta prime precipitates that are growing and are dissolving, and here this is at higher magnification of this area, so you get some idea of what's going on there. And this is a very nice example of the capability to get results useful results from this kind of study, where 2 images taken sometime apart after heating at a couple hundred degrees centigrade, you can see the theta prime dissolving and theta growing very clearly. And if you look at, and here's some other theta primes and the other 2 habits showing up here, and they're dissolving and so on. But if you look at this one at high magnification, so we took these images along the way, and you can see it's just slowly dissolving. And here's the entire sequence where it goes all the way down to fully dissolved. But you notice these features that are, and they're just a little bit of clusters of, and they're out of focus because they're at a different plane than the precipitate itself, but they're kind of blurry, but you can see them. There's still these features that are there. And so we know the orientation of this dissolving precipitate from frame to frame to frame. And if you compare the first and the last, near the last here, you can see that this interface is moving through the lattice as this dissolves, because you can see these fiducial marks. And the interesting thing about this interface, this is just blown up, so you're seeing the pixelation in the 512 by 512 images, but you can tell this is the same kind of structure, so that the interface kind of moves through, but it's very stable. It keeps its structure. Pretty sure that this atom column is not the same as this atom column. It's just that the energetics say that This is the energetically favorable shape of the interface as it moves through the lattice. I can't explain exactly all the details of that, but that's an observation you can make based on being able to do this kind of experiment in the microscope. So we need to start, if we're going to study precipitation processes, we need to start with solution treated samples. So here's an example of a solution treated sample. There's some residual, most of the copper is dissolved, but there's a few large precipitates that are still present, but most of the copper is dissolved into the matrix. And here at 100 degrees centigrade, you don't see any precipitates. And then after 11 minutes at 200 C, all of a sudden you see these precipitates. Okay, so what do we expect the nascent copper or aluminum copper precipitates to look like? So here's typical precipitates in aluminum alloy 206. And what you have are so-called Guinea-Preston zones, GP zone 1 type and GP zone 2 type. This is just a single plane of copper. And this is 2 planes of copper with 3 planes of aluminum in between. So I indicate it like this. See copper, aluminum, aluminum, copper. This is a GP2 zone. Okay, you can have 2 of them together, stacked together. So it looks like a structure like this with three rows of aluminums. So this is all just standard imaging on a bulk alloy. So in our sample, after we did solution treated, this is the 110 zone, heating at 175 C for 60 minutes. All of a sudden we're seeing this kind of precipitate. It's copper, aluminum, aluminum, copper, aluminum, aluminum, copper. So this is not a GP2 zone or 2 of them because it only has 2 aluminums in. Okay, and you can see the difference in the bright field image that you get simultaneously. It shows this kind of contrast, whereas this is the bright field contrast on a GP2 zone. That's a true GP2 zone from the bulk alloy. So there's something going on here. And here's another one that looks like it's actually copper with 4 aluminums, 2 coppers, or 3 coppers with 4 aluminums in between each. And you can see this contrast in the bright field. And another example, because of the contrast. Okay, so this is a different kind of precipitate. Okay, so we call these non-GP2 precipitates. Do they also appear in aged aluminum copper samples like the 206 alloy? Well, of course they do. We didn't know this until we went back and started looking, because we saw these kinds of structures and you just presume, without paying attention, just presume they're GP2s, but they're not. They're this copper, aluminum, aluminum, copper, aluminum, aluminum, copper. So this is just what we saw in the thin foil, and it almost looks like here we have one of the copper with 4 aluminums that's just precipitating now, and here's an example of, in the bulk alloy, that we do have these kinds of nascent precipitates that are non-GP1 or GP2 zones. So this gives us encouragement to try to do further work in using xenon plasma fib technology that we're just installing at Oak Ridge right now. And hopefully in the next few months, we'll be able to do these kinds of studies in much greater detail. So final part, just to show you some examples for the in situ closed cell gas reaction on MEMS devices. I just want to show a couple of examples that give the capabilities of the MEMS device for rapid response experiments and high pressure experiments, and then high resolution imaging. And I don't want to spend a lot of time on the I didn't want to spend a lot of time on the gas cell stuff, because that's going to be the principal focus of Dr. King of Unisic's talk in a couple of weeks. But so now we have a very sophisticated system with a manifold to control gases into a holder that has two chips that encapsulate the gas in between, and a sophisticated controller, the so-called atmosphere system, computer control for doing in situ studies. Kinga will show the movie of the CAD movie of how this all works, so I won't do that. But just to emphasize again, this schematic shows the samples are placed on the bottom side of the heater. So the beam goes through the silicon nitride film, hits the sample material, and then scatters through. So all the resolution happens right here, by the way. So we don't lose resolution. We get noisier images because of scattering, but we don't lose resolution to any significant degree. So to make samples, you deposit powder onto the chip, and here's an example of rapid response. So here's platinum nanoparticles on calcium titanate. Here's the before at 250 degrees centigrade. Then you heat it up for 1 minute to 800 degrees with 50 torr. This is in vacuum. 50 torr, 1 minute, 800 C, quench it. So this is done for 60 seconds. It wasn't done for 61 seconds or 59 seconds. It was done for 60 seconds. And that it's heating up because it goes out of focus. So this was taken in the middle of that 1 minute. The image is immediately out of focus because of expansion, and then back to in focus. And then you can look at the changes that have happened just in that. I think this is pretty remarkable. Just look at the particles of platinum that come out of the lattice and form all over the surface of the calcium titanate. You can't do that with anything other than a MEMS chip heater device. Okay, won't spend time on this. This just shows how the resolution is not degraded by going through the silicon nitride film. But here's an example of high pressure resolution. This is at 8 million X magnification. Basically, this barium silicon or cerium oxide support material. It's platinum doped. We don't see the platinum here in this particular instance, but this is at 35 torr at 500 degrees centigrade with a reducing atmosphere, 8 million X magnification. And then we took it up to 700 torr, almost a full atmosphere, same temperature. And you can see the lattice is barely degraded. Maybe a little tilt happened during that excursion in temperature, but I think it's a remarkable result. You can do high resolution imaging at basically a full atmosphere. I had an example here of nanoclusters, imaging nanocluster movements and gold nanoclusters on titania. But I want to just finish with this example of doing single atom catalysis. Can we do single atom imaging in the gas cell? And this was precipitated by a paper that we did in 2011 that I just checked has been cited this number of times since 2011, one of the 10 most highly cited papers in the first decade of Nature Chemistry. And it's the first time that single atoms were proved to exist and be the controlling factor in doing an improved catalytic, started the entire field of single atom catalysis, basically. So you can look at single atoms of platinum on nickel oxide, for example, in vacuum and over carbon, not degraded. Again, the geometry of the gas cell. And then this is through the silicon nitride and we still see the single atoms with the beam passing just through silicon nitride. And in the full geometry of the cell, you can still see single atoms at 50 torr at 300 degrees centigrade. Reduced contrast, as I mentioned, because of the scattering of the gas, but still single atoms showing up. 15 million X, again, we're right on the verge. So I think it basically shows that there's a possibility that we can even do single atom catalysis studies in the microscope. So just to finish the conclusions, lots of interesting things that can be done with this heating technology. I'll leave this up for just a second. And early work suggests, I just mentioned, particularly for single atom catalyst in situ experiments might be possible. So the contamination is always a problem. I haven't discussed that. Image only at some elevated temperature, if at all possible. And to acknowledge our sponsors and advertise the talk by Kinga coming up in a couple of weeks, where she'll give a lot more details on the gas cell, operation of the gas cell, particularly for incorporating water vapor into gas reaction studies of catalysts that we've developed and published quite a bit on. So that's coming up in a couple of weeks, and I think that finishes the presentation. And ready for any questions that you have.
Larry, thank you so much. It was a really, really good presentation, great insight into a lot of the history that nobody has been able to be privy to, obviously, been there from the beginning. And so thank you so much for sharing that. The photos were really cool. And I know David and John really liked looking at photos when their hair was different colors and it was present,
Yeah.
more so than now.
Well, I can tell you that first example I gave, I can remember vividly when we were taking those pictures, and David and John were there, I believe, and that was extremely exciting when we were just doing the first test in 2007, 2008 timeframe to get those kinds of results, and it was just so remarkable that it was just like a message from God, you know.
Yeah.
Can we do this? Actually, yes, we can.
They talk about those days quite often, and so it's really interesting to learn about. And I know John and David are shaking their heads at what I just said if they're listening. I'm so sorry. We do have a handful of questions though. Let me start with one of the more technical ones that we have here. So from the audience, can we do EELs at the same region of interest that we are doing high-res TEM with the same resolution? What's your opinions on them?
I don't have personal experience doing EELs in the gas cell. It has been done. I believe Kinga does. We have a gas cell system, protochip system, both not only on our 2200 FS, but also on the next door to our lab, we have the FEI, well, thermo now, I guess, Titan microscope that has an EEL system, and that's one of the below the column EELs, and ours is in the column EELs, and so she's done. She can address the question a little better. She's done EELs experiments, and you can do EELs experiments, but they're not quite the same as, because you're going through extra stuff, but you can get EELs results, I believe, from samples inside the gas cell. So again, I don't have any personal experience doing that, so I can't tell you exactly what the details are.
Yeah, it'll be a good question for Kinga. I put a link in the chat for anyone that wants to sign up for hers, and you can ask her that directly. And then if you're curious, you can also respond to your email for the webinar to us here at Protochips, and we may be able to share an example or two with you with some EELs examples in the gas cell. Ray wrote in a good question, which I actually had written down for myself as well. So Larry, with the decades of gas phase microscopy research, what are some examples of research that you'd like to pursue or see pursued that has not been developed yet?
So what's keeping me working, and I just turned 80 last year, is the work that I've been doing with in a major program at Oak Ridge on the studies of aluminum alloys. And we've wanted to do in situ primarily heating experiments, because you don't need gas reactions for precipitation studies, but we do need xenon plasma fib. And we did that early work in 2019, just before COVID was going to start. And we were expecting to get a xenon plasma fib at Oak Ridge, we thought within the next year or so. COVID hit and everything kind of came to a screeching halt. And so we're about, as I mentioned, all of a sudden we have 3 thermo xenon plasma fibs. One is installed at Oak Ridge. I don't really have, it's not really set up for what I want to do. Another one should be installed that I will have direct access to by summer. And so we're proposing a significant program to do fundamental studies of how you do experiments that are electrothermal in nature, because our work is now on EV alloys, using aluminum for electric vehicle applications, in particular to replace copper as a conductor and for electric vehicle applications. So xenon plasma fib to make samples and do fundamental studies of how you can. We don't know how to do electrical measurements. We don't know how to mount samples and what's important. So I want to do a systematic study with some significant funding to do it over the next year if we get it granted. That will keep me around for another year at least. And so that would be exciting. I like to do some of the new and unique things with these capabilities, because that's kind of what we like to do. And so that's my direction right now, and we're concentrating on getting that proposal ready to go. So that's the aim for the rest of my career, which who knows how long it will be.
That sounds like a good focus, though. I hope that you get to explore a little bit of that in the near future. So you've experienced E-TEM with heating holders and now closed cell high pressure types of systems. Is there a time you would choose an E-TEM over a closed cell, or is closed cell, in your opinion, the way to go, particularly for catalyst research with how important the pressure can be related to the results? What are your thoughts on that?
There are significant advantages of closed cell, particularly for not having to have a major functionality of the microscope being to be able to do differential pumping and having things mounted, gas supplies mounted and so on. All you need to do is put a holder in. One day you can do single tilt regular imaging, and the next day you can do gas reactions and up to atmospheric pressure. And then the day after that, you can do double tilt regular imaging and you don't have to do anything in between. Just take your holder out.
Yeah.
And that's a huge advantage of the closed cell work. E-TEM gives you an opportunity to do maybe a little better operando studies. Peter Crozier and his group at Arizona State and their E-TEM can have a catalyst, be studying a catalyst reaction that is done in a holder that has that you're heating up the entire holder in the E-TEM environment, lower pressures, of course, sometimes of which are desired, but they can have enough catalytic material that is in the structure around the grid that holds the sample that they can get actual reactions because of the volume of gas that's around the sample and the whole area is heated up, that they can then start looking at the composition of the reactants, what the reaction is showing. So it's problematical that we would ever be able to do that with even a really sensitive RGA system. That's yet to be determined, I think, with the closed cell approach. So there are pluses and minuses for both of them. We are at Oak Ridge, we're just doing closed cell work at present.
We'll have to show you some recent results where you actually were able to detect in the closed cell with the RGA as well. And so, I'm excited. We've got a nice new workflow recently to optimize that, so we'll have to share some of that with you.
That's good. I haven't been doing that kind of work for several years now. That I moved on to aluminum alloys, and our catalyst funding early on several years ago was zeroed out, and so some of my work on that was leading up to possibly doing those kinds of studies with the RGA system didn't get to materialize. But we've been interested in doing water vapor more than reactants, and so King and I have been working on that kind of capability for quite some time. So we think we know how to do that. She'll explain all that in a couple of weeks.
Yeah. That's a good one too. We'll get you an update here soon on the RGA side. One more question, and then we'll go ahead and wrap up since we've gone a little bit over, but it's the last one. So in your opinion, is gas cell better suited to STEM than for TEM or HRTEM because of limited depth of field, avoids or reduces the effects of scattering after the sample on the information carried by the electron beam? So do you think STEM or TEM or HRTEM is gas cell better suited for one or the other due to possible scattering or due to scattering that can occur?
I haven't done like bright STEM, and doing STEM imaging is best for a lot of studies because you get such high resolution with high angle annular dark field imaging. There are lots of really nice movies and particularly with ETEMs of bright field, aberration corrected bright field TEM imaging and watching what happens. The advantage there is that you can have these fast reactions going on, and you can record movies, not frame by frame by frame and stack them up, but you can record movies that are recording high speed events. So I think they're very. I would love to have an image corrected microscope that would allow me to do in situ bright field imaging to do some kind of catalyst studies on, for example, on samples in that kind of imaging mode. We just haven't done it. And so again, there are pluses and minuses for both capabilities. But overall, the STEM imaging with dark field and sub-angstrom imaging capabilities, particularly for catalyst studies, is still a major advantage for the work that goes on in our lab.
Very nice. Well, thank you, Larry. We did have one more question come in from Arturo, but Arturo, I'm going to connect you with Larry, and we can share your question in email so we can wrap this up because we've gone a little bit over time. But Larry, such an honor to have you here. Thank you so much for preparing a presentation and giving it and sharing the history with everyone here. We really appreciate it and look forward to seeing you, of course, at M&M and all the conferences and such this year.
Yeah, we'll be in Cleveland. We have a paper. Hopefully it'll get accepted.
Great. I'm sure you've got ins there. Yeah, I'm sure they'll work on it.
I've had a few. I think I'm over 150 now, total M&M papers.
I think I can fit one more at this point. Thank you again. I hope you have a good afternoon. Thank you everyone for joining. And any other questions, just reach out to us via email and we can connect you with Larry to get them answered. So have a good day, everyone, or good morning. Bye.
Now I can